Hello everyone, my name is Srikanth, and today I'll be presenting linear function approximation as a computationally efficient method to solve classical reinforcement learning challenges. Reinforcement learning is the study of taking and learning from decisions. We can consider this as a paradigm where an agent seeks to maximize the expected cumulative rewarded gains through interactions with the environment. To obtain this maximum reward, we seek to find the optimal policy that, given some current environmental state, it can return the actions that provide the greatest value. With an effective method to update the policy, this learning procedure should increase the expected reward with each iteration. To optimize our policy, we turn to policy gradient methods. Policy gradient methods are a class of reinforcement learning techniques that directly optimize the policy to increase reward through gradient descent. Policy gradient functions generally optimize a parameterized policy, which is a policy that is represented as a function of vectors. Policy gradient methods generally have a guaranteed convergence for any approximation of the value function and tend to be much more stable than other RL methods. They can also function with or without a model and can make use of model information to thoughtfully define the policy. Currently, the leading policy gradient methods are trust region policy optimization, or TRPO, and proximal policy optimization, or PPO. At a fundamental level, TRPO and PPO share a common goal: to take the largest possible step of policy without risking a breakdown or lack of convergence. To accomplish this, TRPO and PPO take the largest possible step according to the Kullback-Leibler divergence, which is a measure of the distance between probability distributions. TRPO and PPO vary in the way that they accomplish this large step, where TRPO takes the largest possible step within some trust region of the policy, which is computed through complex second-order methods, and PPO applies a penalty to large steps of policy, which is determined through first-order methods. Currently, the reading policy gradient methods use neural networks to parameterize their policy. However, these neural networks are computationally expensive and hard to develop. In addition, we theorize that there are many scenarios where the problem being solved does not necessitate complex architectures such as this. With this in mind, we aim to use linear function approximation, or LFA, as a simpler paradigm to implement reinforcement learning algorithms. We implement LFA by defining our policy pi through a set of features, also called function approximators, and weights for each feature. I also conducted research on the actor-critic method. Actor-critic consists of two parts: an actor that updates the policy and a critic that estimates the value of this policy. In tandem, these two elements combine to develop a system that guarantees convergence for any approximation of a value function. As depicted in our graphic, the critic estimates the value of our current policy and has the actor update the policy to improve the value. A variation of actor-critic exists called natural actor-critic. Instead of using standard gradient descent to update the policy, natural actor-critic uses natural gradient descent. This results in a much quicker convergence to the optimal policy than a standard actor-critic implementation. Our objective can be defined in three parts. Firstly, we should determine whether linear function approximation-based natural policy gradient methods, or LFA and PG, can match the performance of state-of-the-art algorithms TRPO and PPO. Second, we should determine whether LFA and PG can reach the optimal rewards in less time than these leading algorithms. And finally, we should see how all three algorithms react to adversarial noise and discern the level of resistance that they provide. We hope to demonstrate that LFA and PG can match the performance and obtain rewards in less time than TRPO and PPO. Doing this provides support for the use of linear function approximation in a multitude of use cases and broadens the scope of where RL can be applied. In order to develop an algorithm to mathematically determine the optimal policy, we first require some framework to model the problem. To do this, we turn to the Markov decision process, or MDP. The MDP is a mathematically idealized form of the challenge that includes a set of all possible states, actions, and rewards, along with the transition probabilities and discount factor gamma. At each time step k, the agent takes some action A of k, sampled from the policy pi, and depending on the environmental state S of k. It then receives some reward R of k plus 1 and new state S of k plus 1, according to our transition probabilities. Having now formulated a framework for the problem, we then define our objective as to find the optimal policy pi that results in the greatest reward. Within this framework, we now set about formulating our algorithm. We begin by using LFA to define our policy pi in terms of two vectors. The first vector is phi, which is the set of function approximators for the model. Phi takes into account both the state and action. At its simplest, the vector phi for all actions can be described as a diagonal matrix, with all non-zero elements corresponding to a state vector. The second vector is our weights, theta, which we seek to optimize through natural policy gradient methods. We then utilize actor-critic to first estimate the value of our policy and then update our weights accordingly. We now briefly introduce the environments we will be testing our algorithm on. Here, the cartpool environment is a standard reinforcement learning benchmark used over a variety of algorithms. The objective of the agent is to balance a pole atop a cart by applying a force to the left or right. Here we can observe that our algorithm reaches the maximum reward after just 10 episodes. The Acrobot environment consists of trying to swing the end of a two-link assembly above some target point by applying a torque on the top link. Acrobot may be classified as a sparse reward environment, where the positive reward signal is only returned when the agent is sufficiently close to the target. Here we observe that in each training iteration of LFA and PG, the reward gained by the Acrobot increases. Having now designed the structure of our algorithms, we take a step back and analyze our set of function approximators. As we noted, phi contains information about the state and action and also controls the dimensionality of theta. As such, we want to use our knowledge of the environment to formulate a feature set for each application that maximizes the potential of the algorithm. In the cartpool environment, we compare a 4 and 7 dimensional phi. And in the Acrobat simulation, we compare a 6 and 7 dimensional phi. Note that adding too many dimensions would reduce the overall speed of our algorithm and lead to a weaker overall result. But having phis with too few dimensions would lead to a very poor and unstable convergence. Having now determined our optimal set of phis, we begin to compare our algorithms. We begin our analysis of our results by comparing the performance of LFA-NPG with state-of-the-art neural network-based methods TRPO and PPO. We observe that in the carpool environment, LFA-NPG closely matches the performance of TRPO and PPO. In addition, we observe that all methods converge to the global optimum after a similar number of policy iterations. On our sparse reward environment, Acrobat, we observe that LFA-NPG significantly outperforms both PPO and TRPO. We believe that this lower convergence from TRPO and PPO may be attributed to step size constraints from the KL divergence and overfitting from the neural networks. Having now established that LFA-NPG can match or exceed the performance of flagship algorithms TRPO and PPO, we now compare the speed of each algorithm. In the carpool environment, we observe that LFA-NPG takes noticeably less processor time to reach each reward than the more computationally expensive algorithms TRPO and PPO. And within the Acrobat environment, we observe that LFA-NPG and PPO massively outspeed TRPO and run at a similar speed. We now briefly look at the resistance to adversarial noise each algorithm possesses. Adversarial noise describes a scenario where the state used by the algorithm falls within some range of the true state. Within the carpool simulation, we observe that LFA-NPG is slightly less noise resistant than TRPO and PPO, with a drop in performance after a 15% maximum deviation. However, in the Acrobat simulation, we observe that LFA-NPG exhibits a very high resistance to adversarial noise, and in contrast, TRPO and PPO exhibit a higher susceptibility. After observing our data, we may summarize our findings as follows. In standard low-dimensional challenges, natural policy gradient methods such as LFA-NPG reach the optimal rewards in noticeably less time than neural network-based algorithms, while maintaining a similar rate of convergence. And in sparse reward low-dimensional challenges, algorithms such as LFA-NPG converge significantly faster than state-of-the-art neural network-based algorithms, while achieving the same or greater speed. With this, we can conclude that algorithms such as LFA-NPG are effective for a multitude of RL use cases, from robotics to self-driving cars, and often surpass their more complex brethren in terms of performance, speed, and robustness. In the future, we hope to formulate a version of LFA-NPG that can solve problems over a continuous action space, and the self-selected set of function approximators through some linear methods. I'd like to thank my mentors, Sajjad Kodadadian, for his constant support and guidance on my project. I would also like to thank Maria Korshinova and Max Ehrlich for providing me feedback on my work. And finally, I would like to thank the staff of SummerSem Institute for providing me with the resources and tools used to develop my project. Thank you for listening to my presentation.